quickly see if I can share my screen. It says I'm disabled. Screen sharing is disabled, so I think Hannah, I need access to share my screen. Let me just see. Yeah, there you go. I guess
it should work now. I've just made you a host.
Brilliant. So yeah, so just share my screen. I've got a presentation, but before that, I thought I'll take you through like a snapshot of what our journey has been. So Headlight is a startup. We kind of focus on you know, hardware and sort of software solutions for sensing and mapping assets in complex environments or harsh environments, especially the underground. So we came out of Entrepreneur First in 2018, and we started work on putting some devices and sensors on. I mean, we started on a skateboard back then. Quickly moved on and developed a very basic prototype. These was basically built using sort of commercial off-the-shelf solutions, but the idea was to sort of collect data and process that data on the fly in real time. Very quickly, building on some of my PhD work, we looked at, okay, how do we sort of fuse radar and LiDAR to sort of improve sensor performance, especially in poor visibility. And obviously there were plenty of applications from autonomous vehicles of seeing in bad weather to actually putting these devices or these sensors in extreme environments. So we sort of filed our first patent in the late 2018. Then we started working on putting the devices and testing the software on the data that was collected using robots that could actually go into underground culverts, mines, and even sort of wastewater pipes. So we started some trials, and by the end of 2018, we had some investment, and we were sort of we were a headcount of 3. We moved on and we looked at, okay, how we can process this data, and we sort of won a competition with Deutsche Bahn with an aim to sort of capture data in poor visibility from trains to actually do some form of asset inspection, and this was to do with overhead electrical lines. Again, similar idea of processing data from poor visibility, and we had some success deploying some of the technology we were working on sort of edge devices. So two solutions came out of that challenge. One was Slim. Again, this was ideally looking at, okay, what's the minimum amount of data that we need in order to train a really efficient AI model, and how do we quantize that so that we can put it on edge device or edge devices and perform some inference on it. Again, by this time we built a strategic partnership with a company called First Derivatives, and the idea was to sort of look at timestamp data or time series data, and how do we analyze that, which then gave us the capability of introducing dashboards into our offering, and we moved in our entire backend to KDB. And that meant that we were basically processing data with extremely low latency. So this was a very good use case, but the challenges, again, were the same: fast processing or efficient processing in poor visibility. We then had some Innovate UK grants, and I'll touch on that very briefly. There's some, some very interesting challenges there, I'll touch on especially on the Prometheus and Chimera projects as part of the presentations. We then sort of moved on and sort of created a second prototype of our initial sensing solution. So this is multiple LiDARs. It's got onboard motion sensors and some onboard storage and battery, so that we can sort of deploy this on robots and collect the data that we need. This is our most recent design called Telesto. Again, this could go on to drone, onto robots. for locating and mapping assets underground. Again, the concept is to take the data and then process that in the cloud. So that comes with its own challenges. So data acquisition is a big challenge, but data processing is another. So we sort of looked at it from making use of sort of modern technologies, you know, so that we can process them in real time. We do some AI on this as well. So trying to understand the degree of corrosion and cracks. So this is another huge challenge that we faced with the data that we captured. They are not, you're not looking for the targets or the objects that you're interested in don't have a very clear defined shape or set of features. So that and also there's a very limited amount of label data that was made available. So our second pattern, which was looking at addressing this challenge, was by the time we got to sort of getting the data from these pipes, that piece of technology was also already tested on the railway use case, but we sort of then started labeling some of that data ourselves, and we found that there was a huge challenge because the way these data sets are labeled, again, you don't have very simple data sets about cars or people or you know, or trees. These are really complex data sets. So there's a human in the loop that sort of, you need that intelligence to label this data. Sorry, I can hear some background noise. I don't know if that was a question or don't think there is. Okay, I'll carry on. So I talked about Prometheus. I think this is something that might be quite an interest for you guys from a robotics perspective. So Prometheus is a foldable drone that can be deployed through a very tiny hole, which is 150 millimeter borehole. Again, with the idea of deploying it underground so that we can map underground voids or mines. And this, as part of this development, we've developed a very lightweight sort of 100 to 150 grams 3D sensor, and this can be deployed on any drone or any robot and gives you a 360 field of view of the environment you put it in. We continued to sort of address challenges of locating assets, not only sort of understanding what condition those assets are underground, but also trying to sort of locate them accurately, and that was a huge challenge. Now, you may have heard of sort of ground penetrating radar and those devices, but again, those are really ideal for shallow bodied assets, or we are talking assets which are really deep and really long. So that's something is a huge challenge, and that is sort of addressed with Telesto. Again, it's out there in the market, and we're collecting a lot of data, and we are working closely with some of our partners. Where are we going from here? Basically, we, as I said, talked about the 360 time of flight camera system that we worked on. The idea is to sort of commercialize that later this year. So we are going to release that with a set of SDK and APIs to sort of perform basic tasks like obstacle avoidance or SLAM. So this is going to be available. The drone itself is going to be commercialized and be available sometimes later next year. That is still in development, and we're also looking to sort of further grow our team in the following few months. So the theme that we kind of are focused at the moment is to sort of better assess and locate assets deep underground. So that's kind of our journey has been. I think I'm going to switch back to the slides to sort of give you more flavor on the task or the problems that we're trying to solve. So I'm just going to jump straight into like, why are we sort of focused on subterranean mapping? And again, these range from water, wastewater to, again, transportation, and you have deep building foundations. Now, one of the main challenges are obviously there's no GPS, and these environments are quite extreme. You do have risk when you put men down. and it's highly expensive. It is really expensive to do any form of assessment or mapping. So those are like the core challenges that we are interested in, and we've sort of addressed that through Telesto and the Prometheus drone and sort of the lightweight 3D sensing that sort of are our solutions. Now, why would you want to do it? Obviously, you want to improve your operations. You want to reduce your cost. You want to reduce your costs on insurance. Better know where where these assets are if you're going to construct something above ground. And obviously, you want to improve the health and safety and keep workers and public lives safe. Um, how do you do it at the moment? I mean, this is a huge cost, obviously, and at the moment you put men down, and there are kind of ways of doing it. Obviously, you put traditional scanners on tripod systems. These have got limited range, and you don't capture the full asset. So that's a big problem. And you can think of utilities, rail, construction. Everybody benefits from sort of better, understanding where their assets are and on that map. Obviously, there are huge fines associated if you get it wrong, and if you're digging underground and if you sort of bump into a utilities pipe, then that's a huge problem. So where does Headlight fit in? So we basically are interested in any camera. So we have sort of sensor agnostic cameras, lidars, inertial, anything that we work with. And what the solutions are, the offerings are of Telesto that I've touched on, Prometheus, and obviously the idea is to sort of enable operators and utilities to capture that data so that we can process and present it through dashboards. And that's where we're integrating with some of the back-end solutions, and then integrating and bringing on some added value using AI. And on top of that, creating some intellectual property as we go along. This is our team right now, and again, predominantly very technical, but is primarily focused on robotics and in AI. One of the examples of some of the really how bad some of the assets were when we sort of captured them using our device, which was put on a crawler robot. This is another one where you actually see CCTV actually sees nothing because of fog and mist. And again, the idea of sort of combining multi-sensor data and it being independent and on its own and capturing that, and then you can play back or take it in any form of virtual reality. Sort of gives you that flexibility. So we deployed on a platform. It could be a robot, and they deployed. It's on its own. Once it's collected, the data is then submitted, and that's where it comes to our cloud. We process it, we do some QA checks on it, and eventually reports are generated and handed over. So minimum requirement for a human sort of to operate or to deploy, but then you obviously have complexities of data processing on the cloud. I'm just going to skip. So this could be an interesting one for you guys. So speed is a big factor. So how quickly can we collect and how quickly can we process? So this is an example of an 8-kilometer Bournemouth CIS, which we was captured using Telesto, and we sort of digitized and created a digital twin of the asset. And again, over 500 gigabytes of data was collected, but obviously you can then sort of correlate CCTV with point cloud data, and then obviously through our dashboards, you can sort of make measurements of where exactly these inlets are or cracks are. Again, it's a multi-view system, so you get to see assets, in much more deeper. Again, this is one of the challenges that we are working on at the moment is how to fully automate this kind of labeling and sort of machine learning. So this is something. It's a huge challenge right now in terms of the actual labeling. There are different. These are different types of cracks, and at the moment, that kind of granularity is something that is only available when we work with experts in the industry. So that's also another huge challenge compared to sort of traditional labeling data for like autonomous vehicle example, for example. Is another use case of sort of repair. So you've got the old section of the pipe and the new section of pipe, which is lined up. And then you can obviously make sure that it is lined up accurately and you do the measurements. So the idea is that the unit goes through and you collect that data, we post-process it, and then we present this kind of analysis to the end user. Again, things like defects are something that work is ongoing in terms of understanding the variation or the change of shape over time compared to sort of the density of the anomalies. That's an example. Here's an example of sort of understanding what is the degree of exposed aggregate versus calcification. Again, labeling is a big challenge here, and the idea is to sort of continuously sort of train our models on this. So that's also another factor which I think it's more to actually, I'm here to see what the wider community does in terms of the continuous labeling and continuous sort of model training. So I'd be quite keen if anybody has got ideas in terms of how they do it. Is another example of how we combine the sort of surface with subsurface, especially with bends. And this is an open problem right now in this industry, sort of accurately understand where the bends are, especially long distances, and combine it with above surface. So, completely creating a digital twin. This is a short video. Just shows you sort of, you can create fly-throughs through our dashboards and then start looking at the data after you've sort of done that. So again, annotation, taking screenshots. So these are all as part of sort of report generation that the sort of operators and the utilities get. So there are certain challenges that we've addressed. So ease of sort of quickly capturing the data, processing it, and presenting, but there are still open challenges. So a quick summary. Obviously, we provide ways of monitoring and locating. Again, it's better than CCTV. In some cases, it's significantly cheaper compared to sort of traditional approaches. Other sound is an example of using sound. They are quite limited, and it's quite scalable for infrastructure owners. Now we are working to sort of further miniaturize this so that it can go on other robots. And again, this is a technology that is quite independent to sort of the autonomous robotic platform. So it could be basically, it can go on any robotic platforms. And Prometheus drone is something that we've been quite fortunate that we've collaborated with universities. I'm open to sort of see if I can work with other robotic companies, especially with the 360 field of view LiDAR. And further, as I said, later this year, we will be basically, the aim is to sort of release this with an SDK. So I'm more than happy to sort of work with companies to sort of further collaborate on the SLAM aspect. And the Chimera, sorry, very quickly, the Chimera project is something very similar, but this is more on the nuclear for pressure go into pressure vessels, which are or live pressure vessels, which are again on the extreme environment side. And miniaturization is something that is on our minds as well. So I've touched on that. Again, if more than happy for if people want to collaborate, please do get in touch. Sorry, I had to sort of run through this, but I hope it gives you a flavor of the challenges and the solutions we have at the moment. Let me see if I can end it. There you go.
Thank you so much. I was going to ask if anyone has any questions. Did you want about the presentation just then? Did you want to quickly write them up on the chat, and Puneet can take the time to answer if there are any questions at all? Any quick ones, or you can just shout them out, whatever's easier.
Okay. They're incredibly curious. Oh, go for it, Arnav. You're in charge. Go for it.
Yeah, I've got a question. So you mentioned that you're doing recognition of the cracks and that you've got to bring in industry experts right now. So as of now, is it fully manual? Do you hire people to do it for you, or you've got a semi-autonomous where it can detect a crack, but it cannot detect what type of crack it is?
Yeah, I think yeah, thanks for the question. Yeah, it's the latter, but we also sort of hand label a lot ourselves. That's what we sort of started with. But again, cracks are again, we've got the diagonal cracks are the most dangerous ones apparently, and so we kind of detect some of them, but we obviously need the expert to sort of further classify it in terms of what category it comes in. It's the same goes with form of infiltration. So you may have roots, tree roots that sort of come in, and again that sort of is a huge problem. You have different forms of corrosion. Some of it is dried corrosion, some of it is fresh. So you've got these categories where obviously we need these guys help. At the moment, the way the industry does it is they obviously they look at the videos, and the guys are trained. They're trained over believe it or not, it's 190 pages of a course, sort of codes they need to sort of go through and then certified, and they basically provide assigned codes, and that kind of report is submitted. So we sort of are not going to completely replicate that or automate that. It's really, really difficult. But what we're trying to work towards is sort of ease that, and we provide them with lots and lots of detections, and then some of it is sort of filtered through by the expert. That's the idea at the moment.
I see. And yeah, just one last one, once again about cracks. So at what stage, what is the earliest stage that you can detect a crack at? Because there's like crack propagation, and then it grows and becomes bigger. So what is the earliest stage that your device can capture it and classify it as a crack?
Yeah, so far I think in terms of we've pulled up hairline cracks of up to 5 mil. In terms of we've detected cracks to sort of that granularity. Again, it's also the way we capture the data. We don't use a traditional off-the-shelf sort of massive 3D LiDAR systems because it's too power hungry at the moment. So, and also the kind of resolution we get from that is not ideal if you're sort of trying to pick out 5 millimeter cracks. So so in terms of we can I mean they do grow, you're absolutely right, and at the moment we haven't looked at, and that's an area we're quite interested in, to actually see if there are physical models that allow us to sort of see if we can actually model the behavior of these cracks over time. That would be really, really amazing and interesting. But again, I think we'll have to work with experts or engineers or civil engineers from in terms of understanding how that happens. But yeah, if you got ideas or if you got, definitely get in touch.
Yeah, I've got another question, unless someone else wants to jump in or if I'm taking too
There
much
is a
time.
question on the chat. Just see, let me just see. What limitations have you run into in regards to mobile platforms you use to explore subterranean structures? So I think the question is what mobile platforms are. I presume you're talking about robotic platforms that we've I don't know who was Louis. Yeah, it was Louis. If I'm right, I think one of the challenges is that these robotic platforms have to be ATEX, in some cases ATEX rated, or at least robust enough to be put down these environments. The floating platforms, not necessarily. I haven't encountered floating platforms that do need that kind of a certification. But if you talk about crawler robots, these are sort of heavy duty, waterproofed robots. So we can't really be putting our system on really sort of lightweight hobbyist kind of robots because these environments are quite they're quite extreme environments. So that's where we kind of work with some of our partners or operators who have the experience in deploying robots in these environments. There has been some work on the autonomy side in terms of seeing if you can put robots down there which are completely autonomous, but at the moment, a majority of the robots that I've seen in the industry have all been tethered. So there is a scope of some level of sort of semi-autonomy, but I think the autonomous side is still further away in the future. I don't know if that answers your question, but.
My last question was, you mentioned your system is not very power hungry. How do you power up your sensors? Do you take power off of the mother robot, or do you have an inbuilt power system?
Right. So I think yeah, when I say it's not really how long, it's all relative, isn't it? But at the moment, just to give you some context, so the device, for example, the Telesto device, is all everything is inbuilt, the onboard storage, the battery, it's got battery, it's got a range of up to, you can push it up to 4 kilometers in a day. um, um, but so far we've what we've done on, especially on one of the use cases that I've done shown with the 8 kilometers use case, we can easily do 2 kilometers in a single day on that. So again, we're talking about multiple cameras, a couple of lidar systems, and onboard sensors. So it's all powered by the device. But yeah, the idea is because we're working towards the miniaturization version of this, then in theory, yeah, it can take power from the robot.
Another question, if that's all right. This doesn't really seem to fall under consumer electronics. So how do you get a device like this certified? What are the kind of certifications that you have to pursue?
So far, I think it's standard. I think standard electrical and electronics certifications to some degree do apply. I mean, we don't really we use individual sensors which are commercial off the shelf and which should be certified. But what we bumped into in terms of certification primarily is ATEX, and that is explosion proof. But again, those are that's getting something like this. An ATEX approval is an extremely expensive task. And the industry at the moment, I think, it depends on the operators and depends on the asset owners. Some of them are happy with it being non-ATEX, and some of them are quite strict with they won't put a device in their asset if it's not ATEX. But I think it's not impossible, but it's very rare to actually see laser devices being completely ATEX without compromising on the field of view, for example, or the range of the actual sensor. So it does comply with standard electrical and electronic compliance, but ATEX is something is on our mind, and it depends on the client, to be honest. I mean, if there's a massive need, we will definitely get it done.
Okay, that sounds good. Thank you so much. Thank you for the answers.
Perfect. Does anyone else have any questions before we move on to our next guest speaker? Okay.
That's right.
Sorry, was that someone? No,
Yeah,
I
can you
think.
hear me?
Oh yes, sorry, Richard.
Hello, can you hear me?
Yes, we can, Richard.
Hi. I was wanting to know, in terms of search and rescue robotics, I know that's in many ways using something that's able to analyze the structure of a building that's collapsed, or a mine that has a collapse in it. Would you be able to use, I presume it would be able to use in that type of environment, but have you gone down that route yet?
Yeah, so that's exactly where the lightweight 3D sensing solution, which we've called a Dragonfly, comes in, and the Prometheus drone. One of the main use cases we have in mind for that is also search and rescue. If you look at that, I didn't really get that much time to go through it, but the reason why it was born, the idea was born on Prometheus, was the idea of lots of mines along our railway network in the UK. And these mines are all interconnected. So the issue is, if you do have a collapse, then it's a big issue. So you need to sort of map these out, but you don't want to drill too many holes to deploy people or to deploy sensors. So that's where you come, the idea of deploying it through a very small 150 millimeter borehole sort of comes in, and that's where Prometheus drone is, in terms of deploying it through that hole, and the drone unfolds and flies around autonomously. So there's a lot of autonomy that is being developed as part of that. And it definitely has got search and rescue applications, not only obviously with the mining, but yeah, you can also think of recreational sort of divers who sort of go into these kind of spaces. But the drone itself is almost a year away from sort of fully commercialization, but later in the year, the Dragonfly 3D time of flight camera system should be available with some SDKs for for people to try out if you're interested. Yeah.
Yeah, great, thank you.
Perfect. Well, thank you so much. Let's move on to our next guest speaker, Ben from Small Robot Company. Ben, let me just allow you to change your do your screen.
Okay, yeah, got it there.
I think you should be able to show your screen now.
I think I am. Bear with me. Okay. Can you guys see that?
Yeah.
The Small Robot Company slide, just that. Yeah.
Yeah, we can all see.
Excellent. Right. Thank you very much for inviting me along to talk about a Small Robot Company and what we're doing. I'm aware that this is a very smart audience, so I will avoid being too pitchy and talk about some of the details, but hopefully you'll find it interesting. So Small Robot Company is focused on providing a new way of farming, and particularly a new way of farming for the world's largest crops, things like wheat and corn and barley and soy and things like that. And it was founded really off the back of quite a big need. So the thing is about with arable farming, as my business partner, who's a fourth generation arable farmer, found out, is that, well, the starting point is that it's not actually making any money. When Sam came back to his family farm after working at Accenture for a few years, he realized by looking at the books that while the cost of, the yield and the revenues that he'd been generating had pretty much flatlined since 2000. The cost of production had more than doubled in that time. And that meant that his father's farm was essentially going out of business. And he didn't want to accuse his father of being a bad farmer, so he went to speak to a few others and found out this was actually something that all arable farmers were facing. And so this was really what drove him to start looking at what can be done, because it was really clear that what was necessary wasn't a twiddling at the edges, wasn't an automating of existing processes, but a very different system. And then my view when I came into this was understanding that, you know, arable farming in particular, with its use of great big heavy machinery and lots of chemicals to control weeds and disease and pests and the heavy use of fertilizer to make the plants grow, was actually doing a hell of a lot of damage to the soil and to the ecosystem that lived within the soil. Everything from the 2 billion bacteria per teaspoon that you've got, all the way through to the worms and the beetles that ate the slugs and things like that. And this damage to the soil, and also when a crop was harvested, leaving the soil bare at the time of the year when it rained the most, meant that arable farming was essentially creating its own destruction. And this meant that when you had weather events, which used to be freak, but are now becoming the norm, things like flooding events like we had in the UK in the autumn and winter of 2019, or fire or drought or things like that, then arable farming is incredibly susceptible to it. So, oh, sorry. It's incredibly susceptible to these things. So what's really needed is an understanding of how to move forward, how to move past the third agricultural revolution, which was really the invention and use of the tractor and industrial processes of farming and bigger machinery, onto something new that actually is reflective of the technology that's around now, with, you know, our capability to go smaller and more accurate and more precise, and use machinery to carry out lots of very precise things very repetitively. So, sorry, I kind of jumped ahead of the gun here. So just quickly sort of going over this in a bit more detail, I think that we did a survey last year where we spoke to arable farmers to find out how they fared in the 2019 to 2020 winter wheat season, and particularly the bad weather. And of those farmers that we spoke to, 84% of them would have been able to grow their crop if they could have planted earlier. But they couldn't plant earlier because ultimately they were restricted by the weeds that were caused by poor quality soils, particularly a thing called blackgrass, which is resistant to chemicals and can only be controlled by not planting and planting later and using tilling to be able to control it. This meant that farmers had their worst harvest of 40 years. Coincidentally, 40% of their yield was lost in 2019, which is, sort of a huge impact for the staple, the thing that allows you to produce beer and biscuits and bread, and the things that you take for granted, sort of were really at risk just 2 years ago. So as I say, this is really looking at a change, a move from the third agricultural revolution, which we've had with us since the end of the Second World War, which uses heavyweight vehicles like tractors to be able to pull great big pieces of metal through the ground, doing a thing called cultivation, which is basically tearing up the soil to create a seed bed that you can put seeds into, and treating soil essentially like some form of a medium that will grow things whatever happens. And because of these great big pieces of machinery, then hedgerows were ripped out to make fields larger, but farmers still make decisions based on a field. So if they see a small amount of disease in a patch of the field in the corner, they will spray the whole field, and chances are they will spray all their other fields as well, just to be on the safe side. Similarly, if they suffer from cabbage stem flea beetle or something like that in an area, then they will spray that whole field as well, which obviously is hugely wasteful when it comes to chemicals. And this mass application is just really running off from those soils and going into rivers. Also, when you, as I said before, when you harvest and you leave the ground bare, what you allow the rain to do is suck away all the nutrients that are in the soil, or the wind to blow away the topsoil and leave it sort of a shadow of its former self. Sam's farm, for example, has lost 18 inches of soil across his entire farm over the last 30 years. So since 1990, that's probably millions of tons of soil, which have just been washed or blown away. So obviously this is unsustainable. So we viewed that there was a model that needed to come in which was very different, which used lightweight vehicles that disturb the soil as little as possible. They don't compact the soil and they don't tear up the soil to be able to plant the seeds. They use an intelligence which is based on understanding every single plant in the field individually, and only treating that plant when it's necessary, and having that understanding of that plant throughout the growing season. So being able to have this continuous view of what's going on. This allows for this treatment of weeds individually to be taken out, and also treatment of individual plants if they have disease or are suffering from pests. This allows the nutrients to remain in the soil. They're not disturbed or ripped up or washed or blown away, but they remain in the soil. In fact, they can develop and grow because soils do a very good job of healing themselves if you leave them alone, which ultimately creates a sustainable model. To do this, obviously, is not a question of just building one piece of technology. This is a whole new system that needs to be developed, and a whole new system that's based around this model of per plant farming. Now, ultimately, the advantages that we see around per plant farming are so huge that we cannot see how any farmer could not use it by 2040. It is ultimately as big a difference to farming with tractors as farming with tractors was to farming with horses. It is literally a new generation. So when we started speaking to farmers and finding out what their pain points were, particularly around the system at the moment, we realized that selling them farmers wasn't ultimately what they needed. They needed something that they could try, they could see whether it works, and also that they could allow the technology to evolve without them having to spend money on new vehicles every year. So we came up with a system using robots, a platform, if you like, that delivers per plant farming as a service. So this allows us to put a monitoring robot on their farm all the time to gather data, and take that data and run it through an AI engine to be able to determine what needs to happen, and then deliver a service of doing machinery which goes out to the field, and does the job. So doing this, this service is revolutionary. We find ourselves on VC calls where we're asked about who our competitors are, and there aren't any. But yet every farmer that we speak to keeps coming back to the fact that this is exactly what they need. So the way we're doing it is by using a service of robots that we call Tom, Dick, and Harry. And those are held together by Wilma, the brains of the operation. So Tom lives on the farm, completely autonomously, collecting data across 200 hectares of land over the course of 2 weeks, creating 7 terabytes worth of data a day. That data is partially processed on the edge by an algorithm, and then the partially processed data is then sent to Wilma over the cloud, to then convert that into instructions for Dick and Harry. Dick is a robot that just gets delivered to the farm as and when it's necessary, and he does pest, weed, and disease control. But we don't use chemicals in the normal way. We kill weeds, for example, by using electricity to take out each individual plant with a mini bolt of lightning. That allows us to get rid of chemicals in the field completely and allows us to leave the weeds in the field to be able to provide food for the other plants that are there. And we only spray pesticide and fungicide exactly on the plants that need it and where on the plant that's needed, which means that none of that chemical hits the ground, causing damage to the biome that sits underneath the plants. Harry is a planting robot, which plants each seed at exactly the right space and depth for the soil and the conditions, which means that we get the most out of every single plant we put in the ground, as distinct of the 40% wastage that farmers currently have by chucking seeds into a furrow and hoping that some of them stick. Wilma, as I said before, is the glue that binds us together. It allows us to be able to take a view across the field, across the farms, and across all the farms we're working with in a way that other robotics companies don't do, and provides us with a level of per plant granularity that allows us to design our robotics to fit field conditions rather than trying to ape the way that tractors worked before. So ultimately, this has a huge opportunity to increase yields. The existing yields for winter wheat in the UK is 8.5 tonnes. But if you go to the places where they test those wheat plants, they use micro trial plots, which can produce 20 hectares per tonne. And the only difference between those and a farm is they have lots of people in white coats going out and checking each one of those plants to make sure that it's okay. By doing it with robotics, we can get close to that 20 tonnes per hectare on a mass scale, which is 135% increase in yield. Ultimately, this is just the start. If you think about in the US, their average yield for wheat is 5 tonnes per hectare. So there's an opportunity of increasing it by 400%. And in India, it's 1 tonne per hectare. The change that can be brought by introducing the system is absolutely phenomenal. I'd like to quickly tell you a story of one of the robots that we've been developing to get a bit more technical. So when we first started, the vision that we had was we'd have a small Tom robot, a little remote controlled car-sized vehicle that would be able to scamper around and collect the data for us and be very, very light. And this was very popular and led partially to our soft brand and image that we were putting forward. So the first vehicle that we developed was a version of that, if you like. So this is our first Tom robot that we called internally Rachel. And Rachel is exactly what you would expect from an early stage startup. It's powered by the sort of electronics that you would find in any hobbyist kit. It uses a GPS system which is powered and controlled by a mobile phone. And it contains a Raspberry Pi in it to be able to gather the data and process it and being able to give it a geospatial reference, a geospatial pre-processing. So this robot was very effective. We were able to develop autonomy so that it could zoom up and down lines without us having to control it, and gathered enough data with this little Raspberry Pi camera for us to cover 0.1 hectares a day. However, when we started looking into it, we realized this really wasn't enough. For us to be able to cover those 200 hectares, we needed to cover 20 hectares a day or 2.5 hectares an hour. So we clearly needed something that was a little bit bigger, which obviously brought those conversations you would imagine internally about what is a small robot, but we looked at that. So this robot now resides in a permanent exhibition in the Science Museum if you want to go in and see her in the flesh. So we then moved up to something which was capable of covering the distance that we wanted. It had a 6 meter sweep, so the width of the cameras would cover 6 meters. And we used 2 very, very high quality images to be able to do it. It was designed to be 4-wheel drive and 4-wheel steer, so it can turn itself around much more easily. And it was designed to be robust and work in all conditions. Its target speed was 1.5 meters per second, which exactly matched what we needed to do for 2.5 hectares an hour. So this Tom V1.5, we went from sort of drawing board design to robot in the field in 4.5 months. And while it was a very impressive achievement, it also showed. So there were a lot of things, I think, with this version of Tom, which we learned lessons from. It turned out that aluminium head and sort of steer antlers sort of boom thing that we've got there were very heavy, and they pushed the wheels into the ground at the front and made the wheels on the back not so contacted with the ground sometimes. It also meant that the robot was 400 kilos. It meant that the ground pressure of the tires was more than your footfall, which was too big for us. Also, by using small, 2 very expensive cameras, it meant that we were really limited if one of them didn't necessarily perform very well. And unfortunately, one of the disadvantages of using an aluminium lattice setting that we did here was that it does tend to vibrate a lot, which meant that a lot of the images weren't particularly great. So these Tom V1s that we used were not great for their original purpose. However, they've since gone on to be very useful for test beds for other technology that we're using. So off the learnings that we did from that, we then moved forward to be able to develop a robot that could deliver what we were looking for. So the first thing was that we needed to lighten the robot up. So we got rid of that aluminium front end, and we used carbon fiber tubing to be able to get the full width of the boom. The boom had to be wider because instead of using 2 cameras that were very expensive, we used 6 very cheap cameras, which allowed us to be able to get exactly the same amount of data, but for actually slightly less cost, but with a greater chance of them actually taking the photo that was needed. We were also able to put the GPSs on either ends of the boom, which meant that we could get down to our 1 centimeter accuracy that we needed. This robot is half the weight of the previous one, although it's about the same size, 200 kilos. That gives a ground force pressure of about 30 kilopascals, which is the equivalent of 1/3 of your foot on the ground. And with the increased tire size that we're moving to next, that'll bring that down to around low 20s, which means that we can drive across crop plants until they're 1.5 feet high without them damaging them at all. So we decided this was also a good time to move to bodywork, you know, up in the ante on the pro side. However, that sort of size of bodywork was quite expensive to have molded. Also, plastic is not particularly good for the environment. We do have a very strong environmental twist to what we're doing. So we ended up developing the bodywork using expanded polystyrene with an epoxy coat. Now, expanded polystyrene doesn't sound particularly environmentally friendly until you realize it's fully recyclable, which means that we can chop and change our bodywork and grind it up and then turn it into new polystyrene without any environmental impact. So the chassis, rather than being tubular, we moved to using simple pressed aluminium with cutouts. And this got the weight down of the chassis down to 1/3 of what it was before, yet significantly stronger. Also, obviously, using pressed aluminium means it's something that's very easy to cut out and fold and use just using a laser cutter, a folding machine and a rivet gun. Which means that for us to put these together from scratch is a lot easier than if we were using bespoke chassis components. We do need some elements to be bespoke, and this was the lightest possible way that we could implement the way that our legs, as we call them, the suspension and the drive units feed into the chassis without twisting it. So here you can see the robot with the suspension and drive arms on there. Each one of those suspension and drive arms is designed to be able to support obviously this robot around about 200 kilos, but also up to robots that are about 450 kilos with a change of springs. This means that what we've developed is essentially a modular component, which we are then going to roll out across the Dick and the Harry robots as well. They are, as with the previous robot, four-wheel drive and four-wheel steer, which means that we can drive through any mud conditions. They will literally ride over the top of mud that you will sink into because of your great big heavy feet. So here we have, this is at Tharsis, the UK's leading robotics manufacturing plant, where we built our first two robots. And here you can see with the boom in place. So the boom, as I say, is significantly lighter, rather than, I think it was 45 kilos for the weight of the first one. This one weighs in at less than 15, with cameras in place to be able to make it work, and the RTK GPSs at the end. Obviously, when you're dealing with this amount of electronics, it's a very complicated system we need to pull together. So this is to give you an idea of what's required to have the electronic drive and control, as well as the GPS units, as well as the cameras, as well as the pre-processing on board, all fitted into a very narrow and small chassis. So here we are with the bodywork on, some very happy people standing around. This was in January this year. They are socially distanced, I promised. It's just foreshortening that makes it look like they're not. Obviously, we're very proud of this. Now, interestingly, the power of images for a startup. When we went from the Tom V1, the scaffolding Tom, which clearly didn't look like something that you would commercially pay for or buy, to this, and we showed some of the images of this working in the field gathering data for us, we instantly got contacted by 3 of the 6 largest seed companies in the world, who currently don't have a way of being able to detect how well their seeds are doing in field. Do you remember I referred back to before those trial plots where they could produce 20 tons per hectare? Well, the company who produce those seeds that are tested in those trial plots now want to work with us to be able to monitor those trial plots as they grow. This obviously has 2 benefits for us. One is a revenue stream that we can plug into early. The second is we are building a comprehensive data model, a virtual twin, if you like, of each crop variety, which means that we can start getting incredibly delicate decisions based on what we're doing, instead of having to work with data that we collect externally. So that was Tom. What you're looking at here is Dick, the electric reading system. So this robot you might have recognized that we had before. So this is the robot with the electric reading system in place, clearly still a proof of concept. We have underneath 5 arms, which are connected to, you can just about see them, electric probes. And those electric probes are targeted at individual plants in the field. We can recognize the difference between wheat plants and weeds, so we can go out and kill those plants that we need to. And we know the different voltages and levels of power we need to do to kill different types of weeds. But what this has really allowed us to do, the really sort of interesting stuff, is that we can recognize different types of weeds. So we know, for example, that in a standard wheat field, only 40% of the weeds that are in there are ones that you have to kill completely. About 20% of them are neutral, and as long as they don't crowd or outcompete the crop plant, then you can leave them alone. And another 40% of them are actually beneficial, whether they're clovers, who actually lock nitrogen into the soil, or whether they're field marigolds, which provide flowers that encourage pollinators to come into the field. It means that we can create an environment in the field which is less like a green desert, which just has one variety and a bare earth around it, and more like a meadow, which has a number of different varieties of plants in the field, and supported by soils which are full of life as well. In these environments, it means that we have to use less chemicals anyway, and ultimately our aim is to use none at all. So by using these robots, by engaging with Tom, Dick and Harry, it allows farmers to actually move to a point where they are regenerating their soils and they don't need to use those chemicals to grow more crops of higher quality. So I hope that's been of interest. I'm sorry, I haven't got a clock here, so I don't know how I've done on time. But if you do have any questions, please do fire away.
Timing was perfect, Ben. Does anyone have any quick questions they'd like to shout out?
I've got a few. But yeah, please go ahead.
Good. I was going to ask why using robots. I mean, I know this is about robots, and I'm fully appreciative that they are good ones. But certainly for viewing the crop, why not just fly over it with one of these drone things that everyone uses today?
So it's interesting that it's been quite interesting to see the way that the drone industry has sort of risen and fallen in agriculture over the last few years. The problem with drones is that they can only gather in one dimension, if you see what I mean. So they can only see the top of the crop. And they can only see it from a bit of a distance, and they can only see it well if they're in certain light. And when they're up there doing it, they have to have a controller in place to make it work. So for us, we don't need to have anybody there for us to go out and collect the data, which means we don't have to pay for an expensive person to be there, with a strong possibility, bearing in mind the UK weather, that there's sort of 1 chance in 3 or 2 chances in 3 that they'll actually be able to fly that day. The second thing is that for us to be able to detect the weeds with any degree of accuracy, we need to be very close to the plants. The images that we take are greater than 1:1, which means that, so the pixel size is significantly, the image per pixel is significantly less than a millimeter. That means that we can get all the detail around the leaves so that we can understand everything about that plant, which you can't do from a drone. The next thing is that diseases and pests, they don't sit on the top of the plant, they're underneath it, which means that by the time it's visible in the canopy in the top of the plant, the plant's either dead or severely suffering. So it's usually too late for anything to be done then. Whereas we can see underneath the canopy. So we know that disease, like a rust, for example, tends to form on the 2nd or 3rd tiller down, leaf structure down. So we can look there and we can see under the skin using near infrared to see whether there's any cellular degradation. And by doing that, we can tell whether there's disease in the plant before it's visible on the plant, so before it's spreading the disease around. So it's much more efficient. And the final thing is that as soon as the canopy covers the ground, you can't see the ground. So you can't tell how healthy the soil is. You can't tell whether there are any weeds there. So you can't actually derive any benefit. And all this sort of comes together in our sort of big first, I suppose, in that we are the only people able to detect early stage blackgrass in wheat. Now, blackgrass is a £500 million problem in the UK now because it is 70% resistant to all chemicals. It outcompetes wheat plants completely, and it is visually indistinguishable from wheat plants until the seeds are ready to spread, and then it changes colour, and then it sheds its seeds, and then it's too late. So we can detect them as they emerge. Because we're so close to the ground, because we're so detailed, it means that we can take out the UK's biggest threat to our wheat crop straight away.
Cool, thank you. That's a good answer.
Perfect. Are we okay to move on to our next guest speaker? Does anyone have any other quick questions? I know that our next guest has kindly already pushed back his call. So are there any more before we move on?
I've just got 2 quick questions. The first one I have is, has there been any consideration to solar power for these robots? Because I saw that your shell didn't seem to have much in the way of allocation for solar panels or anything along those lines.
No, we wouldn't be using solar panels on the robots. That's a pretty inefficient way of doing it. You can't gather enough power that way. But using solar panels on the kennels for the Tom robots, yes, absolutely. We have been working with the National Trust to develop a small solar site near the placement of where we're going to put our kennels in the Wimpole estate up there, so that we can work out how much we need. Ultimately, for the Tom robot, it doesn't need a huge amount of power, but it does need more than its own surface to be able to do that.
Okay. And then the other question I had was, invariably things always do break down. Nothing ever works perfectly. What does recovery of one of these robots kind of look like when it's stuck out in the field? Because you've kind of put a lot of thought into making sure that your soil is not disturbed and the plants, etc.
Yeah. So the robots are very light, and obviously you can disengage the drive if they completely break down. So for one person, it's perfectly possible to push it back across the field if you need to. But that is very much a catastrophic failure. So we built in sort of very substantial telematics to make sure that we're monitoring everything to do with it. So, the heat of motors, power going through them, charge, all the things that you need to know to see whether or not the robot's working properly. So we can detect issues long before they become a problem like that. As it stands at the moment, we deliver the TOMs to the field at the start of the day, and we pick them up at the end because the kennels aren't quite ready to go yet. But so that means that there is a handler on tap to be able to pick them up if there's a problem. But ultimately, they're connected via LoRa and Sigfox to a robot handler app to be able to pass that information if the robot handler's out of sight.
Well, thank you so much, Ben. Sanford, if you're still there, yes.
Oh, I'm here. I'm here, just being quiet. I know it's not, and unfortunately, the funny thing is that the sun is now coming into my house. Obviously, the weather is changing, so it's good to have that. But let me get my sharing the screen going. Oh, I need to be enabled.
I will just make you the host now.
Ooh, I'm now the host. I'm excited suddenly. Hold on. So allow me to introduce us. Let's do the presentation button. My favorite part of using Google Slides. So it's a pleasure to meet all of you. My name is Sanford Dickert. I am the COO of UV Robots, and also on the call are Arnaud Bissoy, who is our CTO and a student at Imperial College, heavily involved in mechanical design of robotics. And then we also have Mian Ali, who is our chief electrical engineer and also a doctorate in electronics engineering. I had to memorize that because I don't have the details on it. The three of us are here to talk about our project, because what happened was we are a company that was focused on one area of robotics. And then, we had a couple of changes in the world. So let me start. Our original thing was, hey, wouldn't it be cool to develop these serving devices, the robots, into restaurants? Because right now it's becoming a big deal in China, but out here it wasn't really hitting off just yet. A number of the Chinese companies are doing okay, but they haven't really developed service opportunities. Well, suddenly around March of last year, we had something occur. I don't know, but it sort of made restaurants not so busy. And so we said, uh-oh, it's pivot time. So we ended up finding an opportunity. The Innovate UK projects during the time of COVID was looking to create opportunities for individuals to help in disinfecting and all sorts of technologies. And we ended up signing on to develop a low-cost, high-quality disinfectant device that we plan to aim for about 5,000 pounds. To give you an idea, one of the biggest competitors in the space delivers a UV disinfection device at 100,000 USD. And you can see them if you really want to over at Heathrow Airport. But the difference between theirs and ours, we wanted to design something a little bit simpler, easier, and more effective. So there we were. We decided to become UV Robots instead of Robot Tech. We already knew how to do a UV lamp. We had already learned how to do the device for serving, but could we get to this lovely device we want on the right? Well, our requirements were pretty simple. We talked about this, and we wanted a modular system that was configurable with multiple heads because we didn't want to give up our spaces. We wanted to have 3D awareness. Many people just love LiDAR, and LiDAR can go to a certain degree, but the goal was to get to 3 dimensions. Human detection is very important, primarily since UV might have a bit of a problem with humans in the space. We needed to be able to support a length of time without having to plug it in and plugging it out. That's where the battery comes in. We needed to support a heavy load around 100 kilograms that could move at about 2.5 meters per second, but it had to be lightweight and allow for a non-technical person to assemble it. We wanted it to be safe because the ones we had seen were not so in terms of electrics. And like I said, we were aiming for under 5,000 pounds for the entire system. So our first question was, do we build this device or do we buy the device? And so there were a couple of things that we had already investigated. And one in particular is a company called EAI, who built out a platform called the D1. The D1 was originally designed to demonstrate their LiDAR technology. And it's a low-cost, low-cost device that, looks pretty good. Everyone likes to use it. It's got a well-known architecture and software structure. It's particularly sturdy. But during the situation we faced, as in COVID time, there was a couple of problems. Something about supply chain. It was made in China, and the whole goal of the Innovate UK was to do it here in the UK. Assembly of our solution, or any of these solutions, required a skilled laborer to do it. Taking apart the device and putting it together was a bit of a puzzle. It was very heavy, along with a UV module and power bank, because you couldn't connect the power from the base to the UV lamp. That required a lot more weight. And there are other issues associated with it. So funny, all sorts of fun. Just when I'm talking, now all the phones want to make noise. I love this part. Hang on a moment. Let me kill that one too. So we said, well, wait a minute. What about us? We've got some smart people who do mechanical design, electrical design, and so on. They should be able to make this work better. There are some concerns because, anyone who plays with robotics knows the joy and excitement of trying to make something in a short time frame. And we wanted to try something different because since we were worried about issues of stability and strength and so on, we were going to use 3D printing instead of the standard methods of injection molding or other ways of providing that kind of structure and strength. And then, software is always predictable. Well, that was an interesting sound. So our first month, when we got the contract and started going into it, we discovered a lot of problems. I mentioned to you already, but the biggest one that really freaked out the team was the electrical mess that was hidden behind the skirts. It looks really nice, doesn't it? It's a really solid piece of kit there. Challenge, oh my God, you don't want to look in the innards. And then on top of that, there was a couple of other issues that we wanted to make work more effectively. And so this is what we saw. This is what we envisioned. So our design phase focused on the 3D printing, using a revamp of the electrics, improved the motors and battery to support both the lamp and for other heavy objects. We wanted true modularity. As much as everyone says that you can screw something on the top of a base, yeah, we wanted real modularity. Support, and then, as I mentioned before, non-technical assembly. So my favorite part is, why did we use 3D printing? There's a lot of specifics to it, having to do with injection molding is not cheap. It has a lot of other issues associated with it. And Arnav, who's on the call, can speak directly to it. You can see some of the material, the support material, that orange stuff, orange yellow, which is our support that allows for the spaces in between the material that we use for the base itself. And once we solved a few problems there, it was excellent and didn't cost us near as much as the efforts to create the molds for injection molding. On our electronics, Mian and his team basically focused on the schematic design, did a lot of testing, and then we finalized a really efficient PCB design. Sorry, my talking is going bad. Which led to this architecture of the low-level systems. This basically took care of all of the different components within, including, I believe it's 24 ultrasonic sensors, along with the extension with the IMU, as well as the Bluetooth solution and other data channels. You can see the different systems. We also, instead of using the D1, which the D1 was designed to have I believe, Raspberry Pi, we focused on the AT Mega 2560 microcontroller, which essentially, I'm trying to think it's the Arduino base rather than the Raspberry Pi base. Our loop, as well as the different high-level processes we developed that sat within our Jensen Nano computer instead of the Raspberry Pi platform, and ROS. And as you can see, this is how the base was built out. There's a lot of effort on cable management, the design. And if you notice, it's got a little bit of a style to it, kind of like that Tom robot, except we seem to like black and white. I don't know why. Orange would have been really excellent. Our UV system, rather than what we had tested with the D1, was much more modular, literally plugged in, had its own power inverter system together, along with the extended sensors and the lamp itself above. And then we also incorporated both a stereo camera and the LiDAR solution, which gave us much better 3D odometry. And so we went from a simple lamp to, hacked together to what we really desired, and then what we made work. So this system, as I'll show you, we got the base and the system together at 4,400 pounds, 600 headroom to go. And that's only with the prototype, not with production that could be ramped up. Unfortunately, we ended up because we were trying to deliver the solution at the end of April for our Innovate UK project, we have been kind of dealing with documentation and so on. And so the lamp had a bit of a problem with the with a spare wire. So we can't really show you it moving around right now, but we can show you this. We call it the baby steps. Yes, we are proud papas of our device. Our team, actually working out of the Arnav, who's in the center of that, right behind the device, out of his home. And then Mian is the gentleman to the left who has that lovely red shirt. And then I'm the guy, well, you can see. Here's who we are, bunch of guys trying to make it happen. If you'd like to learn more or ask any other questions, you can look at us there or send us emails at our names at uvrobots.io. We are all here for questions.
Thank you so much, Sanford. And audience, does anyone have any questions they would like to ask?
Ooh, we have a question here that says, what kind of restrictions did your client base impose on you, and how does this affect your design choices? When you say client base, are you talking about the fact of the customer segment we were aiming for? Oh, okay. So in a hospital or public area. So the simple sentence was, because we were not being a medical device, we weren't as concerned on that side, but we did focus on longevity. We did focus on, because we're focusing on hotels, restaurants, and companies and hospitals. The challenge with the hospitals is they have a long purchase period. Their sales cycle is between, I want to say, 6 and 18 months. And out here, it's a little more challenging. In the UK, we actually ended up trying to sell it in India, and we were working through that. I don't know what else I would argue or say about this. Arnav and Mian, any things that you'd want to add?
Yeah, in terms of just basic constraints, one is, of course, your robot should be able to maneuver through very tight spaces. because that is a constraint for any place really. Doesn't really matter if it's a hospital or a restaurant. The tighter the space it can maneuver through, the better. The second important one is noise, which we which we ended up achieving by using some passive dampening in the end. The noise is quite important because you don't want it to be very loud. And I guess the most important constraint is that the lamp, since it is harmful for humans as well, it switches off automatically as soon as it detects any motion at all. And you can't just use an off-the-shelf motion sensor on the lamp, because when the robot moves itself, it will just trigger and shut the lamp off. So we had to come up with a different way to make sure that even when the robot is moving, we could still detect other relative motion.
And by the way, just to be clear, part of the reason we wanted to make sure that you could ask some engineering questions. So both Mian and Arnav are excellent engineers as well. So if you want to ask anything about why we chose particular components or particular architectural system designs, we're here to answer. We all are unfortunately somewhat geeky.
Hey, Sanford, Arnav, it's Ben here from Small Robot Company.
Yeah, Ben, go for it.
Yeah, how do you do mapping? How do you know where to go?
So that is with our what do you call it? SLAM technology, along with I'm trying to remember what he called it, the point system. I've got to remember the
cloud.
No, not just point cloud, but he was saying it was millipoint. So one of our engineers basically built out the solution using the ROS path planning technology, and I actually wrote it down and I can't remember. So I apologize. Let me find the name. But Arnav, do you have an answer?
No.
Okay. Yeah, you're not the software guy. We had a software guy that was going to be here, but he ended up not making it. Give me one moment, because I actually tortured him today to go over the architecture and get clarity on it. Let me explain. Let me find it. Software package. So is the multi-point navigation. So the idea is that we did path planning within the ROS system, and the way we did the navigation itself was using a mobile app that provided us with we do the mapping initially to set up the space, using the device, the base and the system itself to map out the location, and then update as it's going through the space using SLAM and other 3D mapping technology within the system. And then what you do is you set your points where you want to go, and it does the via point mapping to it. Does that make sense, Ben?
Yeah, certainly does. Thank you.
Okay.
I think there was one question that's popped up on the chat from
Chhabra. Oh, wow. There's a bunch of them. Hang on. Thank you for the answers. Why was the system spec for 100 kilogram load? Was this to maximize reuse? Yes, because the idea is that making an individual device for an individual situation, in this case, especially in a market that's relatively crowded, as in there's lots of people who make bases and then making solutions in other ways, we needed to find a way to distinguish ourselves with the team that we had and the problem we were solving. And just to let you know, our budget was far less than anything we've ever developed before. Usually you get budgets on the order of $500,000 to $1 million. We were around 100,000 for the entire team and all kit and everything put together. To what extent do we use ROS in our robot? ROS is essentially the communication platform that we're using to do the high level. ROS 2, I believe. Is that right? Do you remember, Arnav? I know it's the newest version. Pardon me?
Yeah, we're using ROS 2.
Okay, so it's ROS 2, pub subbing on all of the different functions that are there. That's why we broke it down to communications, path planning and navigation, disinfection, and then the communication with the handheld app. Okay, sorry everyone, but I need to leave now. Yes, great projects and looking forward to connect with all of you. Sorry, a pleasure to meet you, Puneet. And then are we looking to use other other than Amiga? Hey, Mian, your turn.
Yeah, basically we were using ROS, and ROS has like a lot of libraries available on the Arduino platform. And by using Atmega, you can use easily the You can either program it in using C++, or you can program it using the ROS IDE, and you can have a support for all of those equipment, and you can do it more quickly. So that's why we went with Atmega. But yeah, you can always go for ARM and all of those things. But using Atmega gives you the support of all those ROS Arduino libraries. So that's why we went with Atmega.
Is that the best one you would use, or would you choose any other microcontroller?
For a simpler and quicker solution, a cheaper one, I think I will go with for that Mega for now. Yeah.
Okay. If what do you call it, Rao, do you have any other suggestions? Feel free to speak up, because we're incredibly shy as you're gathering from our little hand off back and forth. Rao, do you have a particular idea of a better solution? Ooh. Rao's gotten quiet. Okay. Does anyone else have any? Okay.
I have a question. Ahmed here.
Hi, Ahmed.
As someone who has built bases before, the question that often comes up buying an off-the-shelf solution is they're often certified, and when you buy one, you have to go through the entire certification to sell it anywhere. So what was your thinking on that?
So
hey,
I got a question. Yeah. When you say certification, what type of certification are you referring to? Because a lot of the bases that you can buy right now would probably be CE certified, but not UL certified. And that is the new one that UK is following. And in terms of electrical safety, we are in the process of getting that as well. But other than that, our major concern for the certification was with regards to UV safety. And from what so when we were developing our static lamps, we talked to a few companies and we found out that there is no clear certification for UV safety. And we had to come up with our own set of tests and work with labs in India to conduct those tests so that we could get our lamps certified. And the best part is you can buy individual components which are certified. For example, the lamps we buy, they're from Philips and they come as CE certified. But as soon as you put it together in an assembly, you have to get it certified again because its UV disinfection capabilities change drastically. Yeah, but other than that, were you referring to a different type of certification?
Sorry, I'm laughing, Ahmed, but I'm guessing you're asking about all of the other aspects like RSOC, and there's another one which is electromagnetic one, and so on. We've been investigating this for a couple of months now, and boy, oh boy, it's so much fun to find nobody who can give you a straight answer. Does that sound familiar?
Actually, what I was talking about, since I'm joining the call from the EU, the EU has a set of standard certification that you can just the EU standards or the CE standards for robot safety. So if you're navigating in a space, you don't hit someone. So
right
along those lines.
So you, go ahead, go.
So I believe as far as CE is concerned, yes, we are looking into it. And also you said a lot of the off-the-shelf components come with it, but that is not true. The robot that EAI sells doesn't come with a CE certification, and you can still buy it. There are loopholes where companies can sell products like that. In terms of navigation safety, that is something that we are yet to look into. We will start looking into it once the navigation is performing to the expectations that we have.
Okay.
But thank you, Ahmed, for asking.
I had a slightly different question as well.
Okay.
So since you talked about it can carry a weight up to 100 kgs.
Yep.
So, but I had a different question, how high can the load be when you put on top of it? So for example, how low is the center of gravity here?
Okay, so for the answer to this is, I believe as of now you can have the load all the way up to 1.3 meters, because our battery is the heaviest component and it is approximately 11 kilograms, and our each motor and gearbox together is around 5 kilograms, and all of this weight sits just 4 centimeters off the ground. So you have a rock solid base, and that this takes away I believe your next question might be, what about if you put 100 kilograms at the top? What happens with vibrations? Because it's a pendulum now, but that doesn't happen because it's such a heavy weight at the bottom.
No, I was talking about like you're assuming it's a uniform base, right? Uniform top.
Yes. So you're saying what if it
Wait, gentlemen, can I make a suggestion? Because now we're going to get into the design. Ahmed, catch up with us and we can go into the design elements and then you can talk about it because Arnav can chew your ear off and give you answers. Does that make sense?
Yeah, makes a lot of sense.
Yeah, you can
send him a private message in the channel because he can give you his email. And actually, it's arnav@uvrobots.io. Okay. Anybody else talk about anything else?
Yeah, I just have a question regarding operating the robots, in spaces. Are you expecting those to be completely human free or not? The reason for my question is, if you're moving along a hotel corridors or something like that, you might choose middle of the morning, early morning or something. But if you happen to bump into a person, I guess you're turning off the lights and things. Mm-hmm. Do you wait for the person to move on? Or do you just move the robot on to another area? And then the question is, do you generate reports at the end of a tracked path to say we have actually illuminated the whole path, and you can give your customers a report saying it's all done or this area was missed?
You want the answer? Your ideas are wonderful. I know that we do handle both non-human spaces, as in no movement, and that we will address human issues, as in that's why we have the human detection and motion sensors. But what you're asking is if you want to extend the offering, which sounds like a wonderful idea, providing a report of the mapping and the tech that happens. Arnav, you wanted to say something?
So we did testing on our lamps, and we know at what distance. So UVC power decreases exponentially, and for us, approximately 8 meters is the diameter, which is where it can still be classed as disinfection. So practically, we could just say that the robot can turn on once again as soon as any living organism, which we do not want to harm, is outside that 8-meter diameter around the robot. And secondly, you talked about, we've already tested a device which maps. We created a theoretical model of how UVC light travels and how we would be able to predict how much of the room has actually been disinfected. But we would rather not just depend on a theoretical model, because even so, for example, when we buy this Philips lamp, it claims a number which in practice it does not match. So you can throw theory out of the window when you start designing such components. So now we're planning on creating a device which does measure actively how much it's called, I think, lumens, how many lumen of light have been delivered and how much disinfection has been achieved. Right. You cannot still get a medical grade result from the device, because for that you have to do a swab test.
That hit your answers, Hayden? Would give you what you need?
Yeah, I think so. I mean, I was more thinking along the lines of, if you're traveling down a corridor and you have to turn the lamps off for a number of meters because there's people in the way or for whatever reason, who will ever know that those few meters were never disinfected? It's not really about the level of disinfection, but the lamp was actually off for this area, and so nothing.
Go ahead.
The simple solution is you just stop the robot and you don't start it again till the person is out of the range, and that way you don't miss out on any area at all.
Okay.
But what I'd say is this: Hayden, it's really good question, and it's really interesting, and I've added it to our channel where we talk about the product features. So thank you for the idea and the insight. It's really appreciated.
Pleasure.
Hannah, you were about to say something?
Yeah, I was just going to ask, is there any other questions that anyone has?
Well, that's great because I have to hang up now to go to my 7:30. So
yes, perfect. Thank you so much, Sanford. I will let you go and I won't keep you any longer. Thank you so much.
no, and thank you all. And Ben, love your presentation. I've had way too much fun with that because I am a big fan of good agency work. I love your narrative and your story. And I basically was talking with the team about this. And I love building robots, but I like building solutions to human problems. And that's been what we've been working on, is working on how to do that. And you came up with some wonderful ideas, even though it is Tom, Dick, and Harry. I mean, my surname is Dickert. And so I grew up with a guy that his name was Thomas Dick and Harry Dick. And I was embarrassed at one point. All I would say, thank you very much for your time and listening to us. If you wish to catch up, we're available online as well. Okay. Have a really good afternoon. Evening, I should say.
Before we end this, goodbye.
You go, Arnaud. I'll see you later.
Yeah, if it's all right, Hannah, I've got one question for Ben before he heads off, because I wanted to ask it earlier, but we were running out of time. So you mentioned something about your aluminum structure vibrating too much, but then you switched it out for carbon fiber, which is stiffer and would vibrate at a higher natural frequency than your less stiff carbon fiber and lead to even more issues with your cameras. How does that work out?
So the challenge around getting rid of the core level of vibration was the suspension system. So we developed a suspension system with a company who consult for Jaguar Land Rover and Porsche and Honda, various rally teams for doing off-road suspension. And so by doing that, we developed a smoothing process, if you like, through the suspension. And then the rigidity in the booms essentially allows for a wave flow with the movement rather than something which is juddery. And the cameras could handle that.
Also, when you moved from your small robot to a big robot to cover more area, did you guys consider just having a fleet of the smaller robots rather than having one big robot?
Yeah, we did. The trouble with the small robot was, I mean, it was very much proof of concept anyway, you know, in terms of the data collection and how close it was to the ground. When we're dealing with wheat, we have to have 70% coverage, 70 centimeter space underneath to allow the wheat crop to pass underneath. So we have to be taller, so we could get all the crop plants. But we really did have a look at potentially doing smaller. And for corn, they have wider rows, but the plants grow up to 2.8 meters tall. So there's a big argument for a narrow, smaller robot there. So we might well go back to the Rachel model for that.
I see. The last one, sorry. So you said it's a service, right? So you don't, the customer doesn't buy it off of you. So you do the maintenance as well.
They pay per hectare per function. So we charge them for if they just want to have tom, or if they just want to have weeding, if they've got a backgrass problem, or weeding and planting, and then weeding, planting, and crop care.
I see.
Yeah, because that allows us to evolve the service as we're going, and stops the farmer from being stuck with hardware which doesn't work anymore. And I'm sure you know the biggest thing for us, because we're out in the field, it's very muddy. You know, it's wet, it's dusty, it's, you know, reliability is a huge problem. So, you know, we know that reliability will come to us over time. It's not something we can rely on being, you know, from the outset.
Yeah, that makes a lot of sense. I asked because of the whole situation with John Deere, where they stopped providing support for all of their fancy tractors in America, and that led to farmers hacking it up.
Yeah, so John Deere's, I mean, it's incredible that a multi-billion-pound company could have such a naive approach to data. The fact that somebody buys your vehicle, you then collect data using that vehicle, but you don't allow the person who's bought the vehicle access to that data, you know, is really, if you pardon the expression, it's really stupid. So they managed to wind up a lot of people. Ukrainian farmers were the hackers. They were absolutely amazing. They took the thing.
Yeah.
But there's also, you know, there are problems with data in farming in lots of places. So there was a company called Climate Core that was bought by one of the big chemical companies called Bayer. And Climate Core originally was a really good system for farmers to be able to do crop predictions. And then Bayer converted it in a way as a way to sell seed and chemicals. And they just the number of users dropped through the floor off the back of it, because farmers, they don't want to pay to be sold stuff. It doesn't make any sense.
Yeah. That's. Thank you for all your answers. By the way, I do ask a lot of questions. I'm sorry for that, but.
Anna, but I was going to say, at the end, I can give you Ben's email address, and any further questions you have, you can ask directly.
It's
yes,
fair.
Of course.
It's as simple as yours.
Thank you so much. All right. Yeah, I won't take any more time. Thank you, everyone, for coming in, and thank you for the discussion. I think it was really amazing.
Yeah, guys, I just want to say thank you so much for joining, and huge apologies for the beginning of the event. Microsoft Live is no longer my friend. I've always used it, and it really let us down this evening. But thank you so much for persevering and joining us. We got there in the end. Obviously, thanks to Puneet and Sanford who have gone. But Ben, thank you so much. It was a great event. I've already had so many messages from people that have come and just left saying they really enjoyed it. So if anyone has any other questions for Ben or myself, feel free to ask now. If not, we hope to see you all at the next Smart in the City event, and I'll be sharing the speakers' email addresses if you have any direct questions you'd like to ask, or myself as well. But yeah, I think we can leave it there.
Thank you, everybody. Thanks very much for organising it, Hannah.
Thank you so much, Ben.
Bye-bye.
Have a good evening, everyone.
Thank you. It was very good. Thanks a lot.
Thank you. Bye.
Bye.
Thank you. Bye-bye.
Bye.
Bye.